All right, in this video we're going to talk about net torque, and you're probably going to hear my really cute son yelling in the background. All right, draw a bizarre apparatus or object. Three masses that are attached to each other by three different lengths of rod. We'll say that the mass of the rods are negligible. And this whole thing will rotate as a rigid body. And to make things fun, let's say that each mass has a force applied to it. Maybe you and three of your friends get together and you decide that you are just going to all hit this thing as hard as you can at different places. Who knows? This kind of will let us see what we mean when we talk about net torque. The idea is simply that each of these forces, F1, F2, F3, at each of these radii, R1, R2, R3, are going to produce their own separate torques, which we can call tau 1, tau 2, and tau 3. Easy. Remember that torque is defined as the component of force that is perpendicular to the radius times the radius. So I could also write this as, can you hear, F1 perpendicular times R1 plus F2 perpendicular times R2 plus F3 perpendicular times R3. All right, now let's talk about those forces and what we can replace them with. Force is equal to mass times acceleration, and each of these objects is going to have an acceleration. But I don't know what acceleration they'll have relative to each other. They're all going to have different linear accelerations because they are not at the same radius from the center, but they will all have the same angular acceleration. And remember that linear acceleration is related to angular acceleration, alpha, or fishy, by multiplying alpha by the radius. So I can rewrite each force equation to be m alpha times r. And when I plug m alpha times r into each of these three force equations, I'm going to need to be careful to make sure that m and r have a subscript. So it would look like this: m1 alpha r1 times r1 plus m2 alpha R2 times R2 plus M3 alpha R3 times R3. Okay, so to go back for a second, remember that the angular acceleration is an angular motion quantity, and all of the angular motion quantities, so theta, omega, and alpha, or the angular position, the angular velocity, and the angular acceleration, all of those things are shared for any object on a rotating body. So like if you and your friend get on a merry-go-round and one of you gets at the center of the merry-go-round and the other goes to the outer edge, you will both have the same number of rotations per minute and then the same angular speed, right? Like revolutions per minute. And if it speeds up, you'll have the same change in how your angular speed changes. So there's no difference in how you're rotating. However, there is a difference in how fast you're going. Your friend at the center of the merry-go-round is going to be going much slower than whoever is at the edge of the merry-go-round, because at the edge of the merry-go-round there is a larger radius, and so you're covering more circumference. So angular quantities, they're always conserved for all the different objects that are in a problem or on a rotating body. Okay, now let's talk about this nasty equation that we've created. Since alpha is a shared value, we can pull it out. And we will have m1, we'll do this in parentheses, m1 times, I'll say r1 squared, plus m2 times r2 squared, plus m3 times r3 squared, all times alpha. So notice I pulled out the alpha and then I squared all of the r's. Okay, if I added a fourth object, m4, at some radius, r4, and a force, f4, what would change about my equation? Well, you would take everything that we just did and add m4 r4 squared times alpha. So there's going to be a pattern, and that pattern is you sum the product of mass and radius squared for as many objects as there are. So we'll write I for that. That's the common notation for sums. All times alpha. So net torque is equal to the sum of mass and radius squared at all points times the angular acceleration alpha. You'll notice that this looks very similar to our net force equation. Net force equals m times a, where, sorry, I wrote a fish. A, where a is your linear acceleration and m is your mass. Or remember, mass is actually your linear inertia. So what we tend to call this is your rotational or moment of inertia, the summa m r squared. The letter that we use for it is I. So that what you'll get, I'm going to get rid of that real quick, is I times alpha. The net torque is the moment of inertia times alpha, the angular acceleration. And it looks a lot like the mass times linear acceleration. Let's do a brief note to make sure that you're getting this moment of inertia thing. The moment of inertia is the sum of m times r squared for however many pieces of mass there are on a rotating body. The moment of inertia is an object's resistance to changing rotational velocity. Resistance to changing rotational velocity. Like here, we have 3 different rotating objects. Notice that there are masses along the rods, and those masses are the same, but they are distributed at different radii. When I release a little tiny bob to rotate this apparatus, you'll notice that the object that has more mass at a farther radius is better at resisting change in its angular velocity. Therefore, it moves more slowly. The object that has most of the mass towards the center of its radius, or closer, smaller radii, it moves a lot faster, and that's because it has less inertia or less ability to resist change in its angular velocity. Now let's take a look at some common moments of inertia. So here we have solid cylinder or disc. This is basically your average pulley. A hoop about its symmetry axis, the red line represents the line that it rotates around. This is basically like a bike tire. And a solid sphere, that would be like a bowling ball. Whereas a thin spherical shell, that would be like a basketball. And then, of course, a rod. You can take a rod and rotate it about different points. Notice that for the rod, it uses L instead of R. Let's see how this works out in just very straightforward practice problems. Your bike tire has a radius of 28 centimeters and a mass of 2.2 kilograms and can be treated as a small hoop. Okay, so right away, I would go ahead and think, all right, small hoop, what is the moment of inertia for a small hoop? Well, if I look up my common moments of inertia, hoop about the symmetry axis, so mr squared. So I'll go ahead and I'll write mr squared. You can use lowercase or capital, it doesn't matter to me. And then off to the side, I'm going to say r is not 28 centimeters, but 19 centimeters, or 0.19 meters. Okay, great. Off to a good start. What constant torque is required to bring it up to an angular speed of 2 revolutions per second in 8 seconds? Okay, that tells me that the time it takes is 8 seconds. The initial angular velocity, you could say omega I or omega f. I'm going to use knots for this one. Omega naught is 0. And omega, the final angular velocity, is 2 revolutions per second. Hopefully you've figured out how to quickly convert revolutions per second into radians per second. Basically, 1 revolution has 2 pi radians. So this would be 2 times 2 pi rads for every 1 rev, or 4 pi radians per second for your final angular velocity. Okay, and it wants me to find torque. That should be a clue that I need to find the net torque, and the net torque is equal to I times alpha. We need to think, can we find alpha from the information that's given? And yeah, we can, because we know that the change in angular velocity over the change in time is the angular acceleration. So 4 pi radians per second minus 0 over 8 seconds is going to give you pi over 4 radians per second squared. That's a terrible S. And I can use that with the moment of inertia. For the moment of inertia, I would do m times r squared, where the mass, oh, I didn't write that down. The mass is 2.2 kilograms. Okay, so I is, I'll just write this here, mr squared times alpha. So 2.2 kilograms times 0.19 meters, the whole thing squared, times pi over 4 radians per second squared. And all of this will give me, oh, wait, maybe you caught my mistake. 4 over 8 is 1/2, so it would actually be pi over 2. Whew, sorry, pi over 2 radians. Anyway, when you put all that in your calculator, you are going to get 0.12 Newton kilogram times meters per second squared meters of torque. Great job.